Hello, good morning, good afternoon, and good evening. Welcome to the MOF 2024 webinar seminar. And today we have our seventh webinar. And before this webinar, I want to briefly introduce the MOF 2024 conference to you. If you are working on the areas of porous materials, especially metal organic frameworks, MOFs, covalent organic frameworks, COFs, and other porous materials like porous cages, this is a conference that you don't want to miss because this is a most well-established conference with close to 2 decades of history. The conference started in Augsburg in Germany in 2008, and then 2010 in France, 2012 in the UK, 2014 in Japan, and that was the first time in Asia. 2016 in the USA, 18 in New Zealand, 2020, because of the COVID, it was held online, 2022, Dresden, and this year in Singapore. So Singapore is it's a city, it's a small, but it's a very great place to have the conference. Here you can enjoy both the good food and the beautiful garden. We have elements from the east and the west, and we'll sure all the participants can enjoy their conference in Singapore. The MOF 2024 conference is held by MRS Singapore and co-hosted by National University of Singapore, the Nanyang Technological University, the Singapore University of Technology and Design, and the Agency for Science, Technology, and Research. So the conference has the themes and the topics of the 5 aspects. 1, materials. 2nd, fundamental phenomena and properties. 3rd, synthetic methods. 4th, characterizations. And the 5th, applications and the industrial integration. This is a conference scheme and dates. We have planned a 2-day pre-conference, July the 13th and 14th. This 2-day conference will be held at National University of Singapore campus. You have the chance to interact and build your network with early researchers. And then starting from July the 15th until July the 19th, we have the main conference. And the main conference will be held at Suntec of Singapore. So these are the brief summary of the conference. We target about 1,000 participants. We have 2 special speakers, Professor Susumu Kitagawa from Kyoto University and Professor Omoyagi from UC Berkeley. So they are the pioneers in the areas of porous coordination polymers, metal organic frameworks, covalent organic frameworks. And we have, including those 2, we have 8 plenary speakers. We have 47 keynote speakers, 79 invited speakers, 163 oral presentations, and more than 680 posters. So this is in the main conference. And we also have the pre-conference, the 2-day pre-conference. And during the main conference, we will organize the editors forum and the industry forum. And we also have the gala dinner and the various social visits. We'll make sure you will enjoy your conference. So this is the editors forum. We have invited editors from different publishers with the flagship journals in chemistry and the materials. I'm sure by interacting with them, you will know more about the publication process, the peer review, and to build connections with them. And besides the editors forum, we have the industry forum, where we invited the industry people from the MOF provider to end users. So by talking to them, you will have a better understanding of what are the current industrial demands in those materials and how, as academia people, we can help to contribute to make sure these materials keep improving our life. So here I want to share with you some statistics. As of April the 8th, we have received 1,040 abstracts. and about a quarter comes from China for obvious reasons, because China is big and it's close by. But we still have a quite large of participants from the rest of the world. We have Germany, United States, and the UK, India, Japan, and Korea, Singapore, etc. So it is truly an international conference. In terms of the themes, the two most popular themes are the materials, theme 1, and application, the industrial integration, theme 5. And beside that, we have received abstract submissions in all the rest of 3 themes. So by attending the conference, you will have a very good understanding about the state-of-art progress in the MOFs and the COFs, in the material, the design, the synthesis, the characterization, and the applications. So as of May the 2nd, we have received more than 730 registration. And I want to highlight some of the social activities. For the pre-conference social visit, we have filled half of the position. We still have some position left. If you're interested, please join us. For the main conference social visit, we are almost full. And for the main conference social visit 2, where you have the chance to visit local carbon capture plant, it is completely filled up. And so does the gala dinner. Okay, so they are quite popular, and we are very glad to see that they have been widely received. So please come and join us. If this is the first time you know about MOF 2024, please visit our website. And we have a social media platform in both the X, formerly known as Twitter, and WeChat. So feel free to look at those, and you can still register for the conference if you have not submitted abstract. As usual, before we start today's webinar, please allow me to introduce our next webinar. So the next webinar will be given by Professor Jiang from Australia, with the title of Engineering the Interfacial Properties for MOF Composites. And this webinar will be held in June 4th, 2024 at 3 p.m. Singapore time. So please register as soon as possible. Okay, so I'm going to introduce today's speaker, Professor Qilei Song. Professor Qilei Song is an associate professor in the Department of Chemical Engineering at Imperial College London, and one of the principal investigators at the Barrier Center. So if you're working on membranes, especially gas separation membranes, you should know the unit barrier. So that is a unit to describe the gas permeability. It was named after Professor Richard Barrier of Imperial College London. So Dr. Song received his PhD in 2014 at the Cavendish Laboratory at the University of Cambridge and stayed for a short postdoc. His PhD and postdoc research was focused on microporous membrane materials for gas separation applications, including polymers of intrinsic microporosity, the metal-organic frameworks, and the porous organic cages. Afterwards, he joined the Department of Chemical Engineering at Imperial College as an Imperial College Junior Research Fellow. So in 2016, he established the Functional Membranes and Energy Materials Group. His research group is focused on the development of porous materials and membrane technologies for broad applications in molecular separations, catalysis, and energy conversion and storage. His recent research was awarded the ICAM-E Nickel Metal and the ERC starting grant in 2019, which provides 1.5 million euro to develop new membrane materials for energy conversion and storage. He is also a co-investor of £6 million EPSRC program grant Sinhai Cell, a virtual UK membrane center on development of high selectivity membranes. He has also established strong research collaborations with industrial partners, including BP, Shell, Toyota Motor Europe, and Schlumberger. So without further ado, let's welcome Professor Song.
Let me share my screen.
Great, the floor is yours, Qilei.
Thank you, Dan, for the invitation. So it's my pleasure to. Can you guys see the screen now?
Yes.
Okay, it's good. So it's my great honor to join this webinar to share our recent research in development of membrane materials, especially porous polymers and metal organic frameworks. So most of our research relates to development of membranes and study the application. So actually, I made minor changes to the titles because I understand this. Most of the audience are probably working on porous materials, and so some of the gas separation work I did earlier may be of interest to some of you. So let me start. So the most of the research we're doing actually at Imperial College are developing membranes for net zero application for energy applications. As you know, membranes are enabling technology for net zero because this is critical for the future because many countries announced they want to achieve net zero emission by 2050, but sorry, that's something wrong. So you need to think about to develop all of this technology, we have to think about how can we advance the membranes in many of the process, for example, in gas separation membranes, in developing membranes for energy storage for batteries, and also membranes for hydrogen production and utilization. So there are some similar challenges. How can we develop advanced membranes to enable the high efficiency of the process and also to save the energy and also to advance the technologies. So our research direction are focused on the development of membranes for these net zero applications from the molecular level design and separation. For example, in the, let me change my screen. So for example, we developed the gas separation membranes and we can integrate them into the membrane module and use them for gas separation. And similarly, in the flow battery device, we need to develop high selectivity membranes and with high conductivity, so we can improve the energy efficiency and use them for grid scale energy storage. And similarly, there are some other challenges, for example, in hydrogen production, especially for next generation anion exchange membrane water electrolyzer, we need to develop membranes and ionomers. So there are some similar scientific challenges. How can we develop this new generation membranes? So actually, my research have been evolved from traditional gas separation membranes to, for example, CO2 capture to battery device. In batteries, you need to have the potassium ion, sodium ion, lithium ion transport, and also into water electrolyzer or fuel cells, you need to have proton exchange membranes or anion exchange membranes. In all of these membrane device or process, you have similar challenges. That is, how can we advance the transport of the gas molecules or the ions and also retain the selectivity towards other species? So our strategy is we develop this new generation of membrane materials, for example, with well-defined porosity, so we can define improve the transport and also improve the selectivity. So it is well known that if you work on gas separation membranes, you know the Robertson's upper bound, for example, there's a trade-off between the permeability and selectivity. So all the traditional membrane materials, they suffer from this trade-off. So our research is we actually develop the membrane materials and the process. So we actually cover a wide range of topics in our lab. So we work on the synthesis of porous materials. We also develop the separation process based on these materials. And we also use some of the membranes, for example, separation membranes or ion exchange membranes. We use them in the battery device. All the knowledge we develop for the separation membrane actually can be transferred to this electrochemical device. We also start work on the energy conversion device, including electrolyzers, fuel cells, and also some other emerging applications. So this is kind of like a one slide summarize some of the progress we made in the past years, including synthesis of new polymers, especially ion conducting polymers, and also development of separation process from these materials. including chemical separation and also electrochemical separation. So we also use some of the materials in the battery device as battery separators or electrodes. And we also designing new membranes and ionomers and use them in fuel cells and electrolyzers. So I want to highlight that actually making the materials, because many of you are working on porous materials, it's really exciting because you need to think about from multi-lens scale. So from the molecular level design, how can we design the materials and based on the different function applications, how can we design the molecular structures of the materials, and also at a nanoscale, how can we engineer the materials, structures, morphologies to achieve high performance? And also, if we do get good materials, how can we manufacture them at larger scale? For example, how can we make the polymers into hollow fiber materials? So this is a big challenge in the membrane community. And also integration of the membranes into electrochemical device. We need interdisciplinary research. So that's why I think in this area it's really exciting, because we have a lot of fundamental understanding to get, for example, on the molecular level, on the structure design, on the transport phenomenon, on the electrochemistry, on the engineering side, we have to look at the manufacturing of the membranes and also the different electrochemical process or membrane process. So I want to give a little bit more introduction to the membrane, to the porous materials and design of membranes. So this is really nice review paper published a few years ago. It summarized some of the key design criteria for new membranes, especially porous membranes. So including properly sized free volume elements and narrow size pore size distribution, and also a thin active layer to improve the flux or permeance, and also highly tuned interaction between permeance and of interest and between the membranes. So this is kind of like a really good, summary of the design criteria. So we actually, a lot of research we are doing has been guided by this design criteria, especially the development of new membranes. So this is another nice review paper published by Andy Cooper. So they summarize the typical porous materials emerged in the last few years. So especially the metal organic frameworks, zeolite, covalent organic frameworks, as well as some other materials, including polymers of intrinsic microporosity and porous organic cages, and also polymer networks. So actually, I was fortunate to have worked on many of these materials during my PhD and postdoc. So I started from the metal organic frameworks. So we develop a mixed matrix membranes by loading these morphs into the traditional polyimides or polymers of intrinsic microporosity. So, and after that, we also work on the PIM polymers and develop some really interesting understanding of these materials, including some of the photooxidation and also some oxidative cross-linking. And I also collaborate with Professor Andy Cooper's group to develop some of the porous organic cages, and we fabricate the cages into thin films. And also we had some interesting discovery on these 2D cage crystals. At Imperial College London, I work with Professor Andrew Livingston. We developed these cross-linked in situ cross-linked PIMS membranes by in situ by interfacial polymerization. So after this, I want to actually give maybe a little bit more details of the work we have been doing on the PIM polymers. Actually, PIM polymers was invented by Professor Neil McCune and Peter Budd 20 years ago. So these PIM polymers are a unique class of materials because they have this unique structures of the backbone structures, very different from traditional linear polymers. Traditional polymers, they have relatively flexibility to move around, but these polymers are so rigid. They have relatively low freedom to rotate for the chain segment to rotate. So And because this is kind of contorted shape of the backbone, when they pack together into the solid state, they form this sub-nanometer porosity. And interestingly, these polymers are solution processable. That means you can dissolve them and cast them into membranes and films. Because of these unique properties of the polymers, they have been redefined the upper bound in the last 20 years, especially the development of new generation of PIMs. So this is a good summary by Professor Neil McKeown. You can see that the PIM chemistry are generally consists of the structure units and a linking group. So they consist of this kind of contorted backbone structure, and also they have a variety of functional groups. So the polymers can be functionalized. So as I mentioned earlier, so these PIM polymers, because of this porosity, and they give very high permeability, so they have been redefined the Robertson upper bound for the last 20 years. So this was the 2019 upper bound. You can see that these PIM polymers give really high gas permeability and also reasonable selectivity. So one of the challenges is the permeability, the selectivity are not enough for industrial applications. So I want to kind of like give a brief summary of the work we have been doing on the separation membranes using these PIM materials. So one of the work I did during my PhD was we actually developed a thermal cross-linking method to cross-link the PIM polymers into with trace amount of ppm of level oxygen at high temperature, not high temperature, maybe intermediate temperature at around 300 degree to 400 degree. So we were able to cross-link the PIMs and enhance the selectivity. So you can see that the CO2 methane selectivity can be enhanced from relatively low level, around 10 to much higher selectivity, around 50 or 60. So the permeability didn't decrease much. So, and based on this work, we also developed the polymer morph mixed matrix membranes. And as many of you are aware of that, morph-based mixed matrix membranes have a lot of the advantages compared to the traditional materials, because potentially they can combine the properties of the morphs, including the molecular sieving properties, the morphs, and the polymers. So in this study, we combined the PIMs and the morphs and developed the mixed matrix membranes. We also cross-link the PIMs, so we got really high permeability and selectivity. So the morphs function as fillers that can enhance the gas permeability. So another study I want to briefly discuss is we also developed the PIMs with the functionalized metal organic frameworks, including the UR066. So because by tuning the interaction between the polymers and the morphs, we were able to enhance the selectivity, because this interaction can rigidify, can enhance the rigidity of the polymers. So then we can improve the selectivity. For example, the CO2 nitrogen selectivity of the PIM1 and the UR66 membrane can be improved to around 30. So apart from the polymers and the morphs, we also did some work on the porous organic cages. So this is the work collaboration with Professor Andy Kruber at Liverpool. So we take some of the porous organic cages and fabricate them into thin films and membranes. We were able to get good performance at the beginning, but these porous organic cages, they suffer from physical aging. So over kind of like after a certain period, so you can see that gas permeance decreased. So at Imperial College, I worked with Professor Livingston during my postdoc. So we developed these PIM materials by interfacial polymerization. So you can say that by combining the PIM monomers with the interfacial polymerization technique, we were able to develop these cross-linked PIM materials. And because they cross-link, so they're stable towards the solvent. So, and we can use this for organic solvent nanofiltration. You can see that this is really exciting because the interfacial polymerization reaction can give 20 nanometer thin membranes. So this really, this is still very great achievement, in my opinion. After almost 10 years, we can see that. So this paper got a lot of citations in the community. So, recently, because we still carry on the work on the interface polymerization. So recently we took some of the new monomers, we combined this chemistry again with the interfacial polymerization. So we were able to further improve the porosity of the membranes. So you can see that similarly, we were able to tune the morphology of the membranes. We are able to get this kind of heterogeneous structures with a skin layer and a porous sublayer. So this is really exciting. We are writing up this work for submission. So another work we have been doing in the past years, we haven't published much. So we take some of the PIM polymers and manufacture them into the flat sheet membranes and hollow fiber membranes. And we are assembling some of these membranes into membrane modules. So this is a lot of work we have been doing, but unfortunately, because we haven't been able to publish, so I'm not going to share much, but hopefully in the future, we can share a lot of the details, how we make these membranes. But generally, this is really important step, because a lot of research groups are making the new materials, but we also need to scale up the synthesis and manufacture them into the membranes that can be used in the industry. So I think this is a critical step that will advance the commercialization of the PIM membranes. So I want to move on to talk about batteries, so especially energy storage. So, but the batteries are different from the lithium-ion battery used in your laptop or mobile phone. So we're talking about flow batteries. So since I established my group in 2016, I decided to change risk topic, because I thought, energy storage is going to become really important, especially we have been developing, renewable energies like solar power or wind power. So this renewable energy are intermittent. So we need to develop larger scale, long duration energy storage technology. So redox flow batteries is a really promising technology for this long duration energy storage. So this is kind of like a diagram showing the traditional vanadium flow battery. So this flow battery is different from the lithium-ion battery. So in the flow battery, you store the electrolyte in big tanks. For example, you have the electrochemical reactions in the cell, but you separate these two chambers by an ion selective membranes. And this you can charge the batteries and with the renewable energy, and you can discharge the battery, release them to the grid. So the volume of the electrolyte can be scaled up, so you can change the energy you stored in the system. You can also scale up the stack, the area of the stack, so you can scale up the power. So this kind of decoupling of energy and power enables the flow battery to be a really promising technology for larger scale energy storage. You can see that. So this 100 megawatt flow battery plant in Dalian. So I visited that in the last 2 weeks ago in Dalian. So there's some challenges in the flow battery. That is the cost of the electrolyte. So vanadium is relatively expensive, and also the membrane used in these flow batteries, like naphthalene membranes, also quite expensive. So if we want to build up for megawatt flow batteries, there's a lot of investment in the membranes and the electrolyte. So there's a growing interest in developing new generation flow batteries with low cost electrolyte, especially the development of organic molecules. For example, you can use this quinol molecules and potassium ferrocyanide. You can also use other low cost metal ions like zinc, or even use hydrogen. So and in all of this material, in all of this new generation flow battery, you can see that you're using two different materials at each site. That means, if the molecules or the materials cross over or diffuse through the membrane, then the capacity will decay. So this is why we need to develop high selective membranes to enable the long-term operation of these batteries. So there are also problems with the batteries in the membranes. So many of the flow batteries currently are using the Nafion membranes developed in the 1960s. So the Nafion membrane is not good. It's very expensive. If you scale up the flow battery plant, you have to use a lot of membranes. It's a huge investment. And also scientific challenge is because the Nafion membrane, they have this hydrophobic backbone and hydrophilic side chain. So when they assemble, when they absorbed the water electrolyte, they form this kind of self-assembled water channels with relatively larger size. That means they're not so selective. So in the batteries, especially in the new generation flow batteries, the crossover of the redox species is a serious issue. That means the battery decay, the capacity will rapidly decay. So we need to develop a better membranes with high selectivity. There's also an environmental concern. I mean, especially in recent years, the PFAS, this kind of perfluorinated compounds, we realize that maybe you have watched the movie called Dark Water. So the contamination, this is a map showing the contamination of the PFAS in the USA. So, and in the European Union, they also have a new policy to regulate the use of these PFAS materials. So we need to develop a new generation of sustainable polymer membranes that solve these technical challenges and also environmental concerns. So this scientifically, this is a big challenge. How can we design new generation of ion selective membranes? So this is another really nice review paper. So summarizing some of the key strategies, so we can tune the pore size, we can tune the interactions and tune the pore length, and also to optimize the operation conditions like electrical field to regulate the ion transport. So guided by this kind of design principles, we actually developed the PIM polymers as ion selective membranes for flow batteries and many other electrochemical devices. So this was kind of like the transferring the knowledge we developed from the traditional separation materials to this new generation of ion conductive membranes. So I want to quickly go through some of the design strategy. Firstly, we developed this hydrophilic functional group for ion conductive membranes. You can see that some of these membranes, PIM polymers, like a Tuger space, because the hydrophilic functionality. So when we develop these materials into membrane, when they absorb water or electrolyte, they become ion conductive membranes. Another strategy is we incorporating these ion conductive groups into the polymers to form charge membranes. We actually have developed several different functional groups, including the amidoxamine, the carboxylic acid, the sulfonate groups. So now I want to share some of the detailed results with you. So actually, so one of the work we did is to use these hydrophilic Tuger space polymers. So this was initially developed by Professor Neil McKeown 10 years ago. They were initially used as guest brush membranes. So these PIM polymers, they can have very high surface area. You can see that the PIM EATB has a high surface area, about 1,000 meters square per gram. So, we were able to tune this backbone structure to tune the surface area, and then we can see that there's a really good correlation between the surface area and the ion conductivity. So, with the for PIM EATB, you can see that they absorb relatively high water molecules, and then the ion conductivity is relatively higher. This means that the water absorption into these polymers, they can form this kind of interconnected water channels that can facilitate the transport of the small ions like sodium or potassium. And these polymers are solution processable, so we were able to cast or spin coat or bled coat these polymers onto the spot. For example, we get the thin film composite membranes. But the challenge is this thin film composite membrane, because they're hydrophilic, so the water transport is is quite significant. So we were able to tune the thickness of these membranes because these polymers are solution processable. So we were able to improve to change the thickness from sub-micron to several micron. And this means that we by enhancing the thickness of the thin film composite membrane, so we actually can mitigate the water transport and also enhance the selectivity. But this is not enough because the polymer itself was not conductive. So we did not get great battery performance. You can see that there's a slow decay because and the polymers, because when we make the polymer into thin film, the crossover of the species is still quite evident. So then we realized that actually the hydrophilicity of the polymer is not enough. We also need to enhance the ion conductivity and also to improve the selectivity. So, and following this work, we also developed the ion conductive PIMs by incorporating these ion conductive groups into the polymers. So this was a collaboration work, including several PhD students in my group, and also Chun Ye from University Animal. So we were actually able to demonstrate this concept using several different PIM materials in collaboration with Professor Neil McKeown. So firstly, we demonstrated the amidoxamine functionalized PIM. So this is a really exciting, very interesting functional group, so that can be protonated at a low pH and also can be deprotonated at a high pH. And very exciting discovery was that because we were planning to use this material in alkaline aqueous redox flow batteries. That means in the high pH electrolyte, these amidoxamine groups can be deprotonated, they become ion conductive. So we were able to establish the relationship between the surface area, the porosity, and the water uptake. You can see that these materials, they absorb the water molecules and form the water channel, and they give decent ion conductivity. Actually, for some of them, AO PIMs in sodium hydroxide, they give comparable ion conductivity as Nafion. And we did detailed study to look at the functional group and also the ion transport mechanism. And we also actually collaborate with Professor Claire Gray at Cambridge to look at to use in solid state NMR to study the interaction between the water molecules and the transport of the sodium in the membrane. So based on this understanding, we actually we were able to demonstrate these membranes in the new generation flow batteries, as I mentioned earlier. So we use this Qilei flow battery as an example to demonstrate these batteries. So you can see that these PIM polymers, they allow the fast transport of small ions like potassium, sodium, or lithium, but they can block the large redox species like ferrocyanide ions. So then, these PIM membranes can improve the selectivity of the membranes and boost the battery cycling stability. You can see that this is the battery performance. And after this work, we also collaborate with Professor Neil McKeown because they have developed a wide range of PIM polymers for gas separation. So we were able to convert the nitrile group to amidoxamine group, and then we can use all of these materials for ion conduction. So you can see that some of these polymers, they give relatively higher conductivity in sodium potassium hydroxide. And then we can integrate these membranes in the neutral pH organic flow battery. We got really good performance. So you can see that by pairing these AOP membranes with the modified quinol molecules, we were able to achieve stable performance over 1 month. So, but the challenge is these PIM polymers, they're really selective. You can see that the diffusion coefficient of these redox species are really low, but the conductivity was not very high. So that limits the energy efficiency of these batteries. So we realized maybe, especially if we want to achieve high energy efficiency in the neutral pH flow batteries, we need to develop some other functional group. For example, the carboxylate functional group that has relatively lower pKa, so the ion dissociation can be achieved at a neutral pH electrolyte. So, so this is the work we did. We converted the PIM1 to carboxylate PIMs. And unfortunately, because these carboxylate groups, they actually absorb a lot of water molecules. So you can see that they show significant spalling and become fully dissolved in water molecules. So this was not good for the membrane development because the membrane swell too much. So then we realized actually we could actually combine the carboxylate PIMs with the amidoxamine PIMs because they derive from the same parent. It's kind of like their brothers and sisters. They have the really good relationship. So you can tune when you mix them together, you got hydrogen bonding and homogeneous dispersion and also very good interactions. So because this carboxylic acid, they can easily dissociate. So then we got much higher ion conductivity. And you can see that, so this is the results. And as expected, by enhancing the ion conductivity, we were able to improve the energy efficiency. You can see that compared to the original AOPIM1, these blend membranes have give much higher energy efficiency in the flow batteries. And also they can retain the selectivity. And we were able to demonstrate that the battery was still able to operate with very high cycling stability. So based on this work, we also developed some other carboxylated PIMs. So we were able to tune the hydrophobicity of the side chain. We got really good performance. So this new generation of the carboxylated PIMs, so they were resistant to swelling. So this is very important because traditional membranes, if you expose that to water electrolyte, they swell. When they swell, they lose the selectivity because the pore size distribution become much broader. That means the redox species will also diffuse through the membrane. So with this new generation of membranes, we can see that they were able to retain the pore size distribution so they can retain the high selectivity. So this was done by the molecular simulation by Professor Kim Jiang. So as expected, if we are able to tune the hydrophobicity and the selectivity of the membrane, we got much better performance. You can see that the battery was able to cycle for 2 months with minimum decay. This is much better compared to the traditional membranes like SPEK, for example. So another work we did was to develop the sulfonate polymers. So this, again, so we were able to perform the sulfonation of this traditional PIM SBF, a classic PIM polymers. By tuning the ion change capacity and the sulfonation degree, we were able to get higher ion conductivity and also reasonable selectivity. So you can see that, so this new sulfonate PIM membranes gives much better selectivity because the membrane, they do not swell too much. And also the optimal membrane, for example, with ion exchange capacity of 1.4, they give much stable battery performance. But there's, of course, if you increase the ion exchange capacity, if you got relatively higher degree of sulfonation, the polymer will swell, and you can see the decay of the battery. So we did some molecular simulation to understand the mechanism because these hydrophobic, initially the PIM, the PIM1 was hydrophobic and some of the PIM SBF was also hydrophobic. But after modification, they become hydrophilic. And once once this polymer absorb the electrolyte, they form this kind of hydrophilic ionic domain. So the size and the distribution of these water clusters are critical to determine the ion transport. So we actually were able to simulate the degree of the different sulfonation and also the hydration level. You can see that, if you got a high degree of sulfonation and a high degree of hydration, the water clusters become connected. You got a fully connected water channel. So the trick is how can we tune the degree of sulfonation and limit the hydration. So based on this understanding, we actually extend the design to a new generation of polymers called PEK. It's a polyether ketone. So this is kind of like in the previous study, we collaborated with DRCP in China to develop this conventional SPK membranes and use them in the flow battery device. But the challenge is this traditional SPK polymers, because they're linear, they have relatively lower free volume. So when you make these materials into ion exchange membranes, you got relatively low ion conductivity. If you want to get high ion conductivity, you have to improve the sulfonation degree to get a very high IEC. So this means that the membrane will swell a lot, then you will lose the selectivity. So with this kind of SPK, sorry, there was some Chinese text. So with this new generation of the tryptophan-based PEK materials, we got intrinsic microporosity, and then we can tune this kind of ion transport with this high porosity, especially the micropore. You can see that you got ion exchange and ion hopping through the these functional groups. So this kind of dual ion transport is very useful. So especially in the alkaline electrolyte, we were able to get very high energy efficiency and retain the selectivity towards the redox species. And when you integrate this membrane into the battery, you got significant improvement. You can see that our new membranes give much higher energy efficiency, and the battery can be operated at very high current density. And to the best of our knowledge, this is the highest to date. And when we integrate this membrane into the flow battery, for example, organic flow battery or zinc ion battery, we always got higher energy efficiency and also decent selectivity, so the battery can be operated for nearly a month. So, of course, there are remaining scientific challenges if we want to apply this redox, for example, membranes into new generation redox flow batteries. We have to think about, especially these alkaline flow batteries, the degradation of these membranes in alkaline electrolyte is a critical challenge. We have to improve the chemical stability of the membranes. And also, if we want to use this membrane in the acidic flow battery, for example, this hydrogen manganese flow battery, we have also developed the membranes that can facilitate the transport of proton and also with higher stability against the degradation by the metal ions. And there are many other flow battery chemistry. So generally, we need to develop the highly conductive membranes to enable the operation of the battery device. So we recently got the funding support from the European Research Council Proof of Concept Grant and also UKI Impact Acceleration Grant. So we are scaling up the synthesis of the membranes, and we're collaborating with DRCP in China because they have this kind of big flow battery stack. So we're going to test our membranes in these stacks. So our flow battery work is really a teamwork. So I want to mention again that so this was a collaboration with many research groups, with my group and also Professor Kim Jeff's group at the Imperial College, and also Professor Neil McCune's group that have been developing these PIM materials for many years. We take advantage of these PIM polymers and convert them to ion conductive polymers. So, and also we did collaboration with Professor Claire Gray and some other groups to look at the fundamental understanding of these materials. So looking forward, we actually are extending the application of the materials to other important applications, for example, fuel cells or electrolyzers. So all of these devices, they have their own scientific challenge. For example, in fuel cells, how can we develop membranes that can operate at relatively high temperature? So because traditionally the nothing membrane will dehydrate when the temperature is relatively high. And also in anion exchange membranes, how can we develop membranes with higher hydroxide conductivity and high chemical stability and mechanical stability? So there are challenges we're working on. Hopefully in the future, we can report the work. As this is kind of like a webinar for the MOF work, for the MOF community, I want to share, before I finish my talk, I want to share briefly the work we are doing on the MOF materials. So we actually have a really exciting work currently under review. We developed this metal organic framework monolith. So we use this soil geosynthesis method. We make this kind of like glass-like MOF monolith. So these MOF materials contain the hierarchical porous structures with mesopores and also micropores. So we because, you know, if you realize that because we have been making these porous polymers as ion conductive membranes, we thought, okay, maybe we can use these MOF materials and make membranes for the battery device. So, but the challenge is metal organic frameworks are relatively brittle, right? So, you know, if you want to make the MOF materials, people normally use mixed matrix membranes, but the mixed matrix membranes are limited by the polymers. Usually, and the transport of the gas and ions are limited by the polymer matrix itself. So we were thinking, can we engineer this MOF monolith into a freestanding MOF membranes or separators? So we actually developed this kind of pressure sintering method to pelletize this MOF monolith into a kind of like dense glass-like heterogeneous MOF pellets. So initially this MOF contains the mesopores, but after pelletization, we can remove this mesopores. But at the same time, we will also densify the MOFs, and some of the MOFs will become amorphous. So you can see that this is a visualization to show that the amorphization of the MOFs. But the advantage is we were able to eliminate the grain boundary in these MOF materials, and we get this kind of dense glass-like pellets. So I call it MOF glass, but actually it's not purely MOF glass. It's kind of like a heterogeneous crystalline amorphous heterogeneous MOFs. So you can see that this is a cross-section SEM image to show the MOF morphology. You can see that it's really dense membrane without any grain boundaries. So when we look at this into high resolution TEM, you can see that the crystalline domain and amorphous domain is kind of like surrounded, this crystalline domain surrounded by the amorphous domain. So this is kind of like the presence of the both crystalline and amorphous structures in the MOF materials. So we believe that this kind of amorphous regions will enhance the selectivity. And we actually did a lot of study of these materials in gas absorption. We found that the selectivity of the gas absorption was enhanced significantly. And because our intention was to look at the ion transport, to use this material for ion transport, we actually compare this MOF glass, this MOF membrane with traditional materials, for example, with cell guard. The advantage of this, because we densify these MOF materials, they absorb a relatively low amount of the electrolytes, but they give really good conductivity and also very high transference number. So you can see that when you compare this ion conductivity with the traditional materials, this MOF material gives much higher conductivity, and also they have higher lithium ion transference number. I have to explain that this is not a solid-state battery, so this is not solid electrolyte. So this is kind of like a semi-solid or quasi-solid electrolyte, because the MOF membrane, MOF separate, absorb a little amount of electrolyte. So this like ion exchange membranes, right? So the absorption of this electrolyte can form this kind of ion transport channel that can facilitate the transport of the ions, especially in the battery. So we were able actually to assemble, the lithium metal battery using this MOF electrolyte. We got decent performance. So you can see that this traditional MOF UL66 powder is transparent. There's a lot of defects and micro voids, so you got relatively low capacity. With this monolithic MOF materials, we can get higher capacity and high cycling stability, because we believe that these MOF membranes enable the uniform lithium ion transport, and they can mitigate the lithium dendrite growth. Okay, so this is kind of like the MOF work. I hope we can share some of the more results when we publish the paper. So looking forward, I believe that these ion conductive membranes and selective membranes, they have broad applications, especially to if we want to apply this material in membrane materials to solve some of the big challenges like energy storage or hydrogen production. So there are many applications, from electrodialysis to batteries to fuel cells to electrolyzers. So, and also I want to highlight maybe there's some other challenges. For example, in the future, it's not just hydrogen, because in Europe there's a lot of investment in hydrogen. I'm sure it may be in Singapore or in Asia. There's also a lot of research going on in this field. So if you look at this hydrogen application, and also a development of other liquid fuels from hydrogen, for example, ammonia. So you have to develop electrolyzers. You also have to think about electrochemical reactors to produce ammonia, or you can dissociate ammonia. So there's a lot of applications, potential applications of the membranes, whether it is electrochemical device or gas separation membranes, for example, air separation or hydrogen separation. And also in the future, I believe this is more important in the future to replace the chemical industry with electrochemical synthesis. So you can see that we are going to develop the chemicals from the traditional to replace the traditional chemical refinery. So this really provides the opportunity to develop the sustainable chemicals and fuels. So membrane technology will have play important role in this electrochemical device, especially electrochemical conversion, and also separation of these chemicals. For example, if you develop a new generation of organic solvent nanofiltration membranes, you can separate the different chemicals. So that means all the traditional separation membranes we develop for the petrochemical industry or other chemical separation can be used in this refinery. So this is kind of like the vision of this. So we actually working together at Imperial College. We are involved in a really big grant, EPSC program grant. We are developing next generation of high selectivity membranes for this high value energy efficient separation process, involving a lot of university in the UK and also industrial partners. So I think it's the time to finish my talk. So maybe because I have gone through a lot of topics, from the separation to energy storage to some of the recent work in the MOF membranes, I hope that you enjoying the talk. So I'm happy to answer questions. So this most of this work done were actually performed by some of the PhD students in my group that actually now have, some of them have initiated their own independent academic career. I'm really proud of this. And also in the work involved a lot of collaborations. I'm not going to mention all their names, but the project also received funding support from the ERC and also some of the EPSC and also some of the industrial partners. So I think then I think I can finish my talk. Maybe it was a bit longer, so I think I can finish and maybe answer questions.
Okay, thank you very much, Qilei, for your wonderful talk. So now it's a very exciting Q&A, and we already have 5 questions waiting on the line. So let me read one by one for you. So the first question comes from Song-Sek Jiang, and he's very interested in the gas separation. And his question is, how do you think about the MOF membrane? I think he's talking about the polycrystalline membrane, not polymeric membrane type. is there any specific regions you study the mixed matrix membrane type?
I think there's a lot of interest, including, Professor Zhou is also working on the mixed matrix membranes. There's a lot of research going on in the field. So my understanding is you need to have a good interface between the polymers and the MOFs. And also there are other new emerging technology being developed, for example, to make the MOFs by interfacial synthesis or in situ coordination. So you can eliminate the ground boundaries in these MOFs. So I believe that you need to develop some new maybe technique to advance to eliminate the ground boundaries, the defects. So I actually personally I haven't done much on the mixed matrix membrane in the past years. We mainly work on the battery membranes, but I think some of the knowledge we develop could be used in the gas separation membranes. Yeah.
I agree, and I think your last part, the pseudomorph glass, is not it's not a glass, but it looks like a glass, right?
It's quite dense. It's actually, I've been talking the sealed glass, exactly the name suggested by Tony, because he said maybe this is called sealed glass, but because we want to avoid the confusion because it's still, there's still some crystalline domain and amorphous domain. So I think it's a heterogeneous morphs, yes. And actually,
that could, that could be a good strategy to eliminate the defects.
Yeah, actually, people have been making the morph glass membranes. There are some really nice study work by the community. So you can melt the morph material into the homogeneous, defects-free. But the challenge is how can we make that morph membrane at larger scale? Yeah.
Yeah, sure. So another question comes from Hussein Yunus, and several questions. What are the key difference between COFs and PIMs? And maybe I will just read one by one so you can address one by one. So the first question, what's the key difference between COFs and PIMs?
Well, the PIMs is relatively, people generally think that it's relatively disordered. It's it's kind of like a contorted, they have contorted backbone, and they can be linear, but they can also be network. But the COFs are more regular. They have crystalline structures. They have much more ordered pore architectures because they're linked by, I think both of them can be linked by covalent bond, but the difference is the PIM polymers, they generally consider it's a linear polymers, but they can also be network type of polymers. Yeah. I think there's some kind of like similarities. They all have the kind of porosity, but because they have relatively different degree of conformation. So the PIM polymers, because they're linear polymers, they can rotate, they have the freedom to rotate and pack together. But the COFs, they are restricted. You don't have much freedom, right?
So next question is, what about the experimental setup for the lab scale testing of redox flow battery of ferrocyanide and the DPPAQ? I think that's a very detailed question.
Okay, so we actually take some of the flow battery device. It's a laboratory cell we got from the USA. It's called Scribner Associates. If you read our paper, you can find the detail. But there are quite a few companies supplying this kind of small laboratory cell. So with effective area between 5 and 25 centimeters square. So yeah, they're actually commercially available.
Yeah. And also the question is, how about the synthesis of PIM condition? I think that can be referred to the published literature, right?
Yeah. So,
okay.
Yeah.
So next question from Abdallah about the mechanical stability. How will you study the mechanical stability?
We actually did study a lot of mechanical property of these membranes, but because in the presentation I didn't show results, but we actually did the stretching test. In some of the membrane, we also did nano indentation to look at the mechanical properties. But generally, these membrane are stable in the electrolyte, but after a long-term operation, some of the membrane will degrade. So we're actually now looking at how can we develop a new generation of polymers with better mechanical properties, with high molecular weight, and also pair the membrane with neutral pH electrolyte, for example, that will also mitigate the degradation.
I see. So Shivani asked a question, does annealing of polyaniline or conducting polymer helps to be used in supercapacitor electrode?
That's not relevant to the work we're doing, right? So, but I think we're not annealing these polymers. We are mainly using these materials, membrane materials, as ion conductive membranes. So you just generally you make these polymers, you cast them into membrane. You don't need thermal processing, so you can use them directly as ion conductive membranes in the device. Yeah.
I see. So Hussein comment, then they are more like a pop. I think the question is the PIMs are more like a pop, right? Polyorganic polymers.
Yes.
I
So
agree. I
yeah.
agree.
Yeah.
Yeah. So actually, I do have some questions for you. So I'm very impressed by your study on the energy storage, like the flow batteries. So from your experience, what are the features that you think are most important for good membranes for energy storage application, especially for the flow batteries?
Very good question, actually, Dan. So you can see that we have in the talk, I talk about several different battery systems. So for each specific flow battery chemistry, because they're using different electrolyte, they could be acidic or they could be alkaline electrolyte. And because these new generation of flow batteries, they're also using different materials. So they're very different from traditional vanadium flow batteries. So in the traditional flow battery, actually, because they're quite corrosive and they very, especially the high oxidation state, they can degrade the polymers easily. So there actually was not many success in developing new membranes for the vanadium flow batteries. But in this new generation of flow battery offers opportunity to apply these polymer membranes because this neutral pH flow battery, for example, they are operated at much mild conditions. So the membranes doesn't need to be so stable. That means, of course, it needs to be stable, but you don't need to have a super stable like a Nafion membrane. So there are several design features you need to consider. That is the stability, the chemical stability, and high ion conductivity and high selectivity in the towards the redox species, and also can be manufactured at a low cost. So actually, been working with group in Dalian, so they actually can make some of the porous membranes using the Zoo-to-Zoo casting machine. They actually been providing these membranes to many other manufacturers. So the scalability, the synthesis is a critical parameter. Yeah.
So I'm wondering how can the porosity help the membrane performance? Because you mentioned the stability, you mentioned high ion conductivity and the scalability.
The porosity, the key challenge is the porosity is to form this kind of ordered channel. Like you do the gas separation, you want to have the suitable porosity, like pore size distribution to enable the small gas molecule to pass through and block the larger molecules. So
Yes.
similarly, in the flow battery, you have similar challenge. So you need to have the small ions like a charge carrier ions like potassium, sodium to transport through the membrane, and these large molecules and their metal ions are blocked. So if you have this introduce the porosity or well-defined porosity into the membrane, you have this kind of very defined pore size distribution. So you have high selectivity and high conductivity.
I see. So you are talking about ion selectivity in the membrane where the pore size should be modified less than 1 nanometer.
Yeah, exactly.
Yeah, because most of the hydrated ions are smaller than 1 nanometer.
Yeah.
Yeah. Another question, or if you don't mind me asking another question, because I'm very curious about this one. Do you know why the batteries start to decay after certain operation? Well, people always show that the performance will start to decay after a certain period of operation, but what's the reason for that?
Well, that's a lot of reasons. In the lithium-ion battery, the battery decays could be due to the many reasons. Could be the SEI, the formation of the solid electrolyte interface, and also the decay and limited by the kinetics of the ion transport, and also the interface resistance, right? So, but in the flow battery, it's relatively easier. So a lot of the decay is due to the crossover. I didn't, maybe I should show some equations, but the capacity is determined by the total amount of the molecules in that can, and the electrons you can charge in the molecules. If you in the one side, if you have the molecules cross over to the other side, then you lose the capacity, right? But there's also other reasons. Is for some of the batteries, if the molecules degrade, then they lose the capacity, they lose the capability to undergo the redox reaction, so they cannot charge the electrons. Then the battery capacity will decay. So generally, there are several reasons for the crossover is a critical issue in this new generation flow batteries, and the degradation of the molecules and the species is another reason for the battery capacity decay. So if you want to limit the battery decay, you need to have actually either way to develop more stable molecules. So this is something we are membrane engineers, so we can't solve the problem. But this there's a lot of research going on in the field by those people working on organic flow batteries. They're developing new generation of molecules that can be more stable, and they you also can develop a relatively large molecule, so the crossover can also be limited. But on the membrane side, you could also develop a membrane with narrow pore size distribution or high selectivity, so that you can also restrict the crossover of the molecules. Yeah.
I see. So in specific for the flow battery, I think probably the stability and the selectivity of the membranes is important.
Yeah, because these are different from the lithium-ion battery, because this flow battery generally you want to operate the battery for 20, 30 years.
Yes.
So you need to have a long-term stability. So this is critical. But I have to explain that most of the research we do in the lab, we try to test the battery over a long period, like 1 month, 2 months, but it's still insufficient. So you actually want to evaluate even longer period. Yeah.
Yeah. So from the porous materials point of view, we need to find a new chemistry that can afford high stability, but in the same time, the uniform and the well controlled the pore size is also very important.
This is why I changed my research topic from morph material to the polymers, because I realized if you want to develop these unchanged membranes, you need to be more stable. So
yeah, exactly.
Yeah. And even in the
Okay.
lithium-ion battery, we actually see some of the degradation of the morph material, because the electrochemical operation conditions are also very harsh. Yeah.
I agree. Okay, so in the interest of time, we will end the webinar here. But I want to say that the membrane is one excellent demonstration of how the porous material can be applied in solving some of the urgent issues. So once again, we highly encourage all of you to come and join MOF 2024 and Qilei. I look forward to seeing you in July in Singapore.
Yeah, see you then. I'm really look forward to attend the conference. Yeah.
Yeah, thank you. Then we ended the webinar today. Thank you very much.
Bye, everyone.